Thanks for the introduction, Adrian. Adrian happens to be my advisor. There's no conflict of interest here. So I guess before we start the talk, I have a couple of things to apologize for. The first one is this hilariously uninformative title, which my reviewers pointed out several times. But I strongly believe that one of the great joys in life is the joy of discovery. So maybe I can do justice to that thought with my talk. The second one is that this is a short talk, so it will not have a bunch of things. For example, it will not have all of the details. We'll definitely not have any formalism, and we'll also not show you any evaluation, right? If you want those things, you can come to my PLDI talk on some of the same topics on Tuesday at 2 p.m. in San Francisco. What this talk does have is some secret new details that you won't get to see in the PLDI talk, and they all relate to how can we generate efficient and correct parameterized design. And if you don't know what that means yet, don't worry, we'll get into it. So here is sort of an algorithm. I'm not going to get into details, but this is how one way to compute divisions on hardware. It's called the restoring division algorithm. And essentially, you have some numbers of bit width w, and you have to apply some function w times. That's the algorithm. F does something, I'm not going to tell you what. There's a couple of ways you can realize this in hardware. First, you can build a fully pipelined hardware design where you stamp out w copies of f, and you sort of stream the data through, and it can sort of process new inputs every cycle, which means it has a high throughput, but it uses up a lot of area on your circuit. The other design is something called fully sequential, which means you pass it one piece of input, and using the same circuit, it sort of processes, it applies f over and over, right? So the computation over f is time multiplexed. We're sort of using the same circuit, and we're using it to perform the same computation for w cycles. This means that this circuit is busy and it cannot accept new inputs every clock cycle. There's also other designs in the middle where you can use two instances and use them for w by 2, and you get the point, right? The design space of something like this is quite big already, right? And so the challenge here is that when you look at this design, all of these modules have the same latency. So if we have bit width 4, we have a latency of 4. But each design has a different initiation interval, which is the amount of, or the number of cycles you have to wait before it can accept new inputs. First design can process new inputs every cycle, the second one every 2 cycles, and the last one needs to wait for the whole input to be processed. And so these timing properties are super important to be captured at the language level. That's one of the theses of this in this talk, that you need to reason about temporal properties of your hardware design explicitly in order for efficient design. If you can't reason about them, you can't build sort of really efficient hardware. It's one of the claims I'm making. And of course, if you get anything wrong, you have to look at this thing, which is really, really sad. But again, efficiency is the driving force. So it'd be really nice if we could have efficiency and correctness both at the same time. And so I'm hoping that by the end of the talk, I can convince you that when building parameterized hardware, you don't have to look like things like these, at least when debugging pipelining bugs. This talk is about a new hardware description language called Filament, which is a language that captures temporal and structural constraints of hardware designs using a type system. Throughout this talk, I'm going to, while I introduce this new HDL, and it'll have to be fast, the thing I want you to note is that at every step, the key difference from other HDLs is that we're explicitly talking about our timing behavior, okay? So a couple of sort of straightforward features in Filament. First thing in Filament is that you take all of your modules and you parameterize them with a set of events. So we're saying here that add has an event G. And using these events, we can specify requirements and guarantees for the availability intervals of all of its inputs. So here we're saying the input left is required in the first cycle, which is represented by the half-open interval G to G plus 1. And the output is also available in that same cycle. This is what makes adders combinational. Don't worry if you know what that means exactly. Similarly, we can give a type signature to our multiplier, and the multiplier takes several cycles to produce its outputs. So now we have sort of distinguished, we've captured the fundamental difference at sort of the physical level between the adder and the multiplier. The adder can produce outputs immediately, the multiplier takes several cycles. So we've captured some temporal properties of our design. The second thing that Filament does, and we all have to do when we're building fast hardware, is we have to think about pipelining, right? So normal sort of sequential designs have to wait to process an entire input first before they can process new inputs, but of course in hardware design, we want to pipeline things. And so one other thing that Filament does is it captures this property called the initiation interval, which again is the number of cycles you have to wait before you can accept a new input. And this is a structural constraint. Once you build a piece of circuit, it is doomed to have that initiation interval forever and ever. So we need to capture it, we need to reason about it, we need to reason about it for composition purposes. The way Filament does it, it provides a very clean and concise encoding of initiation intervals. All you have to do is specify a delay for an event. You have to say, this event can happen every 2 cycles. And so now we have captured this fundamental property about the multiplier, that it processes new inputs every 2 cycles. It has a latency of 3. And so Filament has a type system, which again I will not get into, but at a high level, when you write programs in Filament, it enforces 2 properties. The first one is that a well-typed program only reads semantically valid signals. And by that I mean you never violate one of these timing constraints on your inputs and outputs, which means you have balanced pipelines. The second one is that well-typed Filament programs don't have any resource conflicts, which means you don't have any structural hazards when you're running your design at the initiation interval you specify. And because of this, Filament can rule out a large class of pipelining bugs at compile time. So using this, I'm going to show you an extension we've been working on for Filament, where we can do parametric design that has all of those properties at compile time that allows strong composition principles. So we're going to work with this design called a shift register. A shift register is something that takes an input in the first clock cycle and delays it by n cycles, right? And it does it by a chain of n registers. So first, we're going to look at the signature of the shift register. First thing to notice is that the input is accepted in the first cycle, output is produced in the nth cycle, and the shift register can process new inputs every cycle. Without even seeing the implementation, you know now how to use it efficiently. You can give it new inputs every cycle, and you know you have to wait n cycles. And if you don't, Filament has a type checker that will give you error messages at compile time. Next, the other thing to notice is that when we build one of these shift registers, that signal is in the first cycle. Once it goes through a register, it's delayed by 1 cycle, so it's the second cycle, the third, and the fourth, and so on, right? And so if we generalize it to a parametric design, for each wire, the signal is available at the kth cycle. So if you've gone through k registers, that signal is available in the kth cycle. And so the way we express this in Filament is this weird, complicated looking thing that says, I have n plus 1 wires, and for the kth index into that array, this is an array, the type of the wire there is this, which means this wire is available at the kth cycle. It's essentially encoding the fact that the kth wire is available in the kth cycle. This, again, is like a complicated thing, and feel free to ask me questions, but this is the sort of keystone in making everything work. Next, once you have this, you can sort of define a bunch of connections between circuits. So you can say the 0th wire takes the input in. And again, this will type check because in is available g to g plus 1. We replace k with 0. We get the exact interval we wanted. Next, we can use a for loop to instantiate a bunch of hardware. So we have a loop going from 0 to n, and when we're instantiating n registers. Nothing special about that. New is just a keyword that we use to describe instantiations because I'm a PL person. And then the final other part of Filament that we use to specify timing behavior of things is called an invocation. An invocation says that I'm going to use this register in the g plus ith cycle. Invocations are sort of different and unique in Filament because they allow you to specify some control flow using this high-level structure. And then we're saying that when I run this register in the ith cycle, I want to give it the input f of I, which means take the ith wire and connect it into the ith register. Right? And this makes sense because, again, we're building this chain of registers. Finally, we said that the output from that register is the input to the next register. And then the output from our design is the output from the last wire. Okay? Again, there's lots of stuff going on, and don't worry if you don't get the whole program. The high-level thing to understand is that this signature will be correct because Filament will check this body to ensure this signature is what it implements. Right? And if you do something wrong, it will give you somewhat nice error messages that look like this that tell you where things are going. The outcome of this is that because Filament has this type system, it will enforce that no matter what values of n you give to the shift register, it only reads semantically valid signals, and it has no resource conflicts. And it does it in sort of a polymorphic way, which means Unlike C++, where you instantiate the template and then you get error messages. But like something like SMO, you look at the definition, you prove the definition is correct for all values of n, and then you never have to check the body again at use time. So it's a very powerful guarantee that we get at this point. I want to wrap up by showing you how we give the signature to the divider implementation that I was talking about. I'm not going to show you the body, that's complicated. But here's sort of the trade-off div. Let me go into each part. So a divider takes 3 parameters: the bit width, the number of instances of f you want, and the number of times you need to reuse them. And then we say there's a constraint that I times r, which means the number of instances times the number of times each instance is reused, is equal to w. This is needed because we need to apply f exactly w times. Next, we can look at the output, and we know the latency is w, because it's captured right here. Finally, we can look at that delay, and we know the initiation interval is r, which means if you have a design that reuses each f 2 times, that is your divider needs to wait 2 cycles before providing inputs. And so now you have this divider that has a very complex trade-off space. You can build fully pipelined, somewhat pipelined, fully sequential, and everything in the middle. And what Filament, and there's an implementation, I just want to scare you a bit, but don't read it. But at the end of the day, you can look at the signature, and you can build all of these designs and know that they're correctly pipelined for a strong definition of correctly pipelined. I want to end this talk by giving you one other pitch for why parametric design and type systems are a good fit. So one thing you would notice if you ever use something like the Berkeley hardfloat library is that it gives you purely combinational designs. And this is because they want you to take the design, put registers at the end, and retime it for your use case. So for example, my design might run at a low frequency, so I need to only add 1 register, whereas someone is building like high performance hardware, they might put 6 in there, right? And so what is the interface for something like this, right? It has a functional interface, but what is its timing behavior? Well, in Filament, we're exploring the idea of using existential types, where we can say there is some latency that the outer world doesn't know about, which will be decided at compile time. And so the outer world must sort of use this value of L and be abstract with respect to that. So when you use this FP add, everywhere in your design, you have to use that L, right? And what this means is that when you go in and fix the value of L, your entire design will reconfigure and be correctly pipelined. And if you change that value of L because you weren't meeting your timing goals, it will again reconfigure itself and be correctly pipelined. So I want to wrap up. And so there's this sort of trade-off that we've been talking about the whole time. There's modularity and efficiency. And as PR people, we've sort of explored a bunch of points on the modularity axis by building DSLs and trying to give you a compiler-based sort of approach to modularity. But a lot of the state-of-the-art sort of industrial languages pick efficiency, and they pick it by really having to give you sort of a low-level way of reasoning about timing. And so Filament is this other approach where you have to encode a lot of information in your type system. You have to prove to it that what you're doing is correct. But once you do it, you get a fast hardware design. And so this is very similar to the pitch that I think Rust makes, which is that you have to work a lot with this borrow checker and this complicated type system. But when you can do it, you get fast hardware or fast software that's correct. But in Filament's case, fast hardware that's correct. This is Filament. Thanks for listening to my talk. If you're curious about these things, you can go to filamenthdl.com. As Adrian said, I'm on the job market. Happy to take questions. Thanks.
This clapping we're doing right now is for all of the speakers we just heard about in this segment.